My name is Caitlin Fix, and this is the first lab for Physics 2212, where we'll be analyzing charged tapes. The purpose of this experiment is to create charged pieces of tape by quickly pulling apart the U-tape from the base tape. This causes each tape to acquire an excess or deficit of electrons. From there, we will analyze the interactions between two U-tapes, and finally, estimate the excess charge on a single piece of tape. Throughout this experiment, we will be continuously using two assumptions. The first is that each tape has the same net charge, with that charge evenly distributed across the tape. The second is that each tape can be simplified to a singular point charge, allowing us to use the point charge electric field and force formulas. As you will see, this experiment demonstrated that the U-tape was negatively charged, with an excess of 6.4 times 10 to the 10th electrons on a single piece of tape. Additionally, the comparison between observed and coded calculations are extremely similar, if not identical. For this lab, we will utilize a couple of fundamental physics principles. The first is Newton's second law, which says that the net force is equivalent to the mass of an object times its acceleration. The second is Coulomb's law, which describes the electrical relationship between two point charges. Specifically, it states that the electrical force is equivalent to K, or 1 over 4 pi epsilon naught, times the charge of Q1 times Q2 over the magnitude of r squared, all times r hat. The last two pieces of physics are the force of gravity, which is the mass of an object times the gravitational constant, 9.8 meters per second squared, and the electric force, or rather, another way to write the electric force, which is the charge of a point charge times the electrical field of the other point charge. Now we're going to move into the actual data collected during this lab. The length of the tape was 0.22 meters long, with a width of 0.02 meters. Using the assumption that the tape is 1 gram per meter, we can find the mass of the tape by multiplying 0.001 kilograms by the length, giving us a mass of 0.00022 kilograms per meter. Additionally, we calculated that the distance between the two tapes was 0.021 meters. Moving forward, we observed that the two U-tapes repelled each other, whereas one of the U-tapes and a neutral object, in this case a book, were attracted to one another. Furthermore, given a situation of a negatively charged pen, we predicted that if the U-tape were positive, it would be attracted to the pen. Similarly, a neutral U-tape would also be attracted to the pen. A negatively charged U-tape, however, would be repelled from the pen. After rubbing a plastic pen on a shirt and placing the tape near it, we found that the two repelled each other. Thus, the U-tape must be negatively charged. Before performing calculations, we're going to answer a couple of experimental questions. Using Newton's second law and the observation that the tape's momentum is not changing, we know that the net force in the y direction is 0. The two objects that contribute to this force are the force of gravity and the electrical repulsion between the two U-tapes. In addition, to find the gravitational force, we need to find the mass of tape B, which we previously identified as 0.00022 kilograms per meter. You can see the force diagram for tape B to the right, modeled as a point charge. The electrical and gravitational forces are in opposite directions, but with the same magnitude. Now we have all the information we need to perform the calculations. First, we're going to find the gravitational force by multiplying the mass of tape B by the gravitational constant, giving us an answer of 0.002156 newtons. Next, we need to find the charge on tape B. Because the net force is 0, we know that the force of gravity is equal to the electrical force. Since we only need the magnitude, we can set them equal to each other and solve for Q. At the end, we find that tape B has a charge of 1.028 times 10 to the negative 8. From here, we can find the excess number of electrons on tape B by dividing the charge on the tape by the charge of a single electron. This yields an answer of 6.416 times 10 to the 10th electrons. Now, we need to find the total number of atoms on tape B, which can be done by dividing the surface area by the area of an atom. This gives us an answer of 4.4 times 10 to the 17th atoms. Finally, we can use the answers from the previous two calculations to identify the ratio of excess electrons to atoms, which turns out to be 1.458 times 10 to the negative 7 electrons per atom. That concludes the calculations we needed to do by hand, and now we can check all of our work by establishing some code. This includes defining our constants and reducing our tape to point charges, along with defining a function that calculated the electrical field when given the observation location and charged particle information. Furthermore, we typed out all of the formulas that we used to perform our calculations, and finally, created arrows that can demonstrate each force. As you can see in this final product, the diagram mimics the free body diagram from before perfectly. Additionally, the outputted answers from our written code directly parallels the answers received when we calculated each value by hand. Before coming to the end of the lab, we have a couple of reflection questions to answer. The first asks, what would happen if electrons suddenly turn positive and protons turn negative? The answer, absolutely nothing would change. The charges on the U-tape would still have the exact same magnitude, the only difference being that they are positive. Additionally, they would both have the same sign and thus repel each other. Therefore, none of the interactions would change. The second question asks, why is it important to handle the charged tape as little as possible? What happens when the charged tape comes into contact with other objects? Well, the charged tape on its own contains an excess of electrons. When it comes into contact with a neutral object, like a hand, the electrons will begin transferring towards the less negative object, or the hand. This slowly creates an equilibrium between the tape and the neutral object, rendering the previously observed interactions useless.